So I'm going to tell you about how we use or how we try to use astronomical spectroscopy to probe changes in the fundamental constants of physics over cosmological time. And this is the GMRT, the Giant Meter Wave Radio Telescope near Pune, which it will turn out will not be part of this talk at all, but I just like it very much, so I'll show it to you. Okay, so this is a broad outline of the talk. I'll try to tell you why you should care about the possibility of changes in fundamental constants at the start. And of course, the easiest way of telling you why you should care is via quotes. And you can always rely on Feynman for a good pithy quote. And so that's one from Feynman. The fine structure constant alpha, the value of the constant, is one of the greatest damn mysteries in physics. Schwinger was not known for good quotes. And in this case also, he doesn't have a good quote, but it's much more pithy than Feynman. That's Schwinger's car. That's a Flavia Lancia 962 model, which I've taken the liberty of redshifting. He used to have a powder blue car, but notice the license plate. So that was his license plate for about 7 years while he was in Harvard. And which kind of tells you a little bit about the fact that, given that in the States, your license plate tells you a lot of the person, how important alpha was to Schwinger as well. So I will tell you a little bit about the basic technique. How does one use what principles go into measuring fundamental constant evolution, and I'll tell you a little bit about atomic clocks as well, but I will focus mostly upon cosmological redshifts via what are called redshifted spectral lines, and this will be broad background, and since I thought I should present you some new results, new at least about a year old now, I decided to focus on the hydroxyl OH molecule and tell you a result that we've gotten using what are called conjugate satellite OH lines at redshift of 0.25. I'll tell you where we are, and I probably won't have time to tell you where we want to go to, but there's lots of time for questions. So why do we care? Before we start with why do we care, the question arises, what are fundamental constants? So fundamental constants are basically free parameters of a theory. That's a fairly agnostic view of the subject. They're quantities which quantify your ignorance about physics. They're quantities whose values cannot be predicted from within the confines of the theory, but which have to be measured and then put in my hand. And obviously, this will immediately tell you that the fundamental constants of, say, the standard model are not the same as that for classical electromagnetism. But examples of fundamental constants are the quantities such as the speed of light, the electron charge, the reduced Planck constant, the fine structure constant alpha, E squared upon h bar c, the ratios of particle masses, and so on. And I've chosen, for a good reason, to indicate two of these in magenta, or two good reasons. One reason is that these will be the focus of the talk. The second reason is that, unlike these three parameters, these two are dimension-less quantities. These are dimension-full quantities, and I will try to convince you that one needs to focus on dimension-less quantities while trying to probe changes in the constants. So if you like, our favorite theories today are the standard model and GR. And you can quantify our ignorance about the universe by stating the fact that there are 22 free parameters in the standard model and GR. We have no idea why these parameters are the values that they have. But more critically, we have no idea, beyond assumptions, whether these parameters are indeed constant. These are assumptions in the standard model and relativity. So a pragmatic view for tests of changes in the fundamental constants is that there's simply a test of the basic assumptions of the standard model and relativity. You're just testing the assumptions of your favorite theory. And these are similar, for example, to tests of local position invariance, Lorentz invariance, violation of the equivalence principles. All of these are assumptions built into these theoretical models, and you test them. However, perhaps a more interesting point of view is that changes in the low energy coupling constants, quantities like alpha, are expected, and I've intentionally put expected in quotes, in higher dimensional theories that attempt to unify the standard model and relativity. And this is a fairly generic prediction. I will not go into why it comes up, but it's a fairly generic prediction of these unification theories. And this is interesting because most of the predictions of unification theories are actually at extremely high energy scales, that is a 19 GeV or so. So what you really want are low energy predictions, and fundamental constant evolution is an example of a low energy prediction which might give you a way to push beyond the standard model. And so this gives you a low energy probe, and which is why we like it a lot. What's the catch? The catch is that the very genericity of these predictions tells you that you don't know the time scale on which these constants change. They could change on timescales of a day, or they could be secular changes on gigayear timescales. And what this tells you is that you must now test for changes on all timescales ranging from days to gigayears, to the age of the universe. And so that's where astronomy comes in, because astronomy gives you access to extremely large look-back times over billions of years, which you can't get in the lab. And I've tried to convince you that this makes for a lot of fun, if nothing else. Okay, so how do you go about this? The first thing to take home is that you must test for changes in dimensionless constants. So for example, alpha, or the ratio of the particle masses, and this avoids confusion with units, because the definition of a unit often implicitly assumes that a parameter doesn't change. For example, the definition of the kilogram was changed recently, last year, so as to include the assumption that the Planck constant doesn't change. The speed of light has been assumed to be constant in the definition of the meter. So you want to work with dimensionless quantities. The approach is fairly simple. You measure a single quantity, which could be, for example, time or redshift, some observable, some measurable, with two methods. The crucial thing is that the two methods should have different dependencies on the constant in question. So for example, two clocks of different materials, which have different dependencies in which the transition on which the clock is based has different dependencies on alpha. If alpha changes, you simply plonk these clocks down in a vacuum and monitor them. If alpha changes, one of the clocks, which say has no dependence on alpha, whose frequency has no dependence on alpha, will simply keep plodding along. Its time will keep going along steadily. But if the other clock, if its transition depends on alpha, and if alpha changes, that clock will drift, will go fast or go slow relative to the first clock. So what you need is two methods which have different dependencies on a constant. And since I've emphasized, and if the constant changes, the two methods or techniques will give you different values for the measured quantity. The beauty of atomic clocks, of course, is that, of course, you're measuring time. You have high sensitivity, which is lovely. But most important, you have great control and systematic effects. You actually build the clocks. And you place them in this field. You can do all kinds of stuff to stabilize them against external effects. But the catch is that the only probe changes in timescales of 1 or 2 years, which is a tiny fraction of the age of the universe. So although you get great sensitivity and great control in systematics, you can only probe short timescale variation. And that pushes you towards astrophysical or geological techniques. So I'm going to focus on one particular astronomical technique using spectral lines. And that's based on measurements of the cosmological redshifts of galaxies. And of course, the redshifts are because of the expansion of the universe, and more distant galaxies have higher redshifts. The further the galaxy is, the higher its redshift. And this is where things become interesting. The fact that the speed of light is finite means that you're observing these distant galaxies as they were in the past. So for example, a redshift of 0.1 corresponds to about 1 billion years ago. A redshift of 1 corresponds to 8 billion years ago. A redshift of 6 corresponds to about 12.8 billion years ago. Which means that if I can identify a galaxy at a redshift of 1 and measure two redshifts from two spectral lines which have different dependencies on alpha, I can actually test for changes in alpha all the way out to 8 billion years ago. That's the game, basically. So how do we do this? The way you do this, specifically, is that the line rest frequencies depend on alpha, mu, and so on, and you have different dependencies for different mechanisms. For example, we find lines which are fine structure lines, hyperfine structure, rotation, inversion, lambda doubling, a whole slew of lines. Every one of these mechanisms gives you a different dependence. So what you need to do is to find two lines from a single galaxy with different mechanisms, which give you different dependencies on alpha, and now simply go and measure them. And that's where the fun starts. And the way you do it is that, so if lambda observed and lambda rest are the measured and the lab line wavelengths, the redshift is defined by this trivial equation, lambda observed is lambda rest times 1 plus z. But this implicitly assumes that lambda rest does not depend on redshift. You're assuming over here that you can apply the lab wavelength to the galaxy at redshifts of 1 or 2 or whatever. So suppose we say that alpha depends on redshift or on time. That means that lambda rest depends on time. What this means is that you'll put the wrong value of lambda rest in this equation, you'll measure lambda observed, and you'll infer the wrong value of z over here. So fairly simple. Now if you take a second line, you will again infer the wrong value of z, but it'll be wrong in a different way. So those two wrongs, if you like, will give you two estimates of the redshift, and you're looking to see if the redshifts match or not. So if alpha changes, two lines from a galaxy with different dependencies of lambda rest and alpha will give you different redshifts of the same galaxy. So the game is very simple. You just identify two lines with different dependencies of lambda rest on your favorite fundamental constant. You go outside, find these lines in the galaxy, you take your favorite telescope, go very deep on the galaxy, and that's it. And check. There's a catch, as always. The catch is that a galaxy is not a point particle. A galaxy is a big object. It's a nasty object. It does all kinds of nasty things. It's got turbulence, it's got rotation. And gas clouds inside a galaxy are moving at speeds of tens of kilometers per second. In fact, within the cloud, you'll have speeds of kilometers per second. Right? Now, this is bad news, because this means that you're measuring a redshift over here, but these internal motions of a few kilometers per second would add delta V by C, where delta V is a few, of the order of 10 to the minus 5 to every measured redshift. Which means any difference that you see between line redshifts could simply just be the motions of the gas. So how do you get around this? And that's been the hard part of the game for a long time. It turns out that you can show that up to factors of order unity, delta alpha by alpha will be of the order of delta Z upon 1 plus Z, so of the order of delta V by C. So you wind up with a sensitivity limit which is about 10 to the minus 5, and you can't go better than this. The ways around this are twofold. One way is to just take a lot of lines. Take a lot of lines because some gas will go in this direction, some gas will go in that direction. There's no preferred orientation in the universe. Average. Statistically, things should work out. This is not a great thing because in an ideal world, you would like to be able to trace the evolution of alpha. If alpha does change, you'd like to actually probe its evolution with redshift. You'd also like to test for spatial dependencies in alpha. So the other possibility is to use what I would call special lines, where the line physics is telling you, is guaranteeing that the lines arise from the same gas. So if you can come up with such lines, you're in business. Because now you'll have a local measurement at some redshift, a redshift of 1 or 2 or whatever, and you have an in situ measurement of delta alpha by alpha. And that's wonderful. The question is, can one find such lines? And of course, the answer is that yes, we can. Otherwise, I wouldn't be here. So the reason we love radio, more than say optical or ultraviolet, is that there are molecules in the radio. Molecules give you lots of spectral transitions in the radio, and there are different types of transition. There are complex molecules like OH, which I'll tell you about a bit more, ammonia, methanol, whose transitions are extremely sensitive to changes in alpha and mu. So for example, ammonia has inversion transitions. Methanol has a whole bunch of mixed transitions, which are tunneling, plus rotation, plus vibration. And OH I'll tell you about. And this means that you can use different lines from one molecule. The different lines from the same species can actually be used to probe changes in alpha. Now that's cute, but that requires that the gas is in thermal equilibrium. If the gas is not in thermal equilibrium, you're back to square one because one line might be excited in one part of the cloud, the other line in another part of the cloud. You're done. You're sunk basically. So in thermal equilibrium, the lines would be the same velocity, and there's been a bunch of papers in the last 15 years coming up with theoretical ways of doing this. The other nice thing in the radio is that you have this remarkable frequency calibration with errors which are less than 10 meters per second, and we can get to less than 1 meter per second if we wanted. That's good news for us. In the optical, it's about 2 orders of magnitude worse than this. The two best techniques today are what are called conjugate satellite OH lines and methanol lines. I'm going to focus on conjugate satellites today. And both of these have the property that the lines are special in that they come from the same gas. And you can test for this, which is why it's nice. So what is the hydroxyl molecule? So the hydroxyl molecule is a completely boring common or garden molecule in galaxies. It is the first molecule, in fact, which was identified in the interstellar medium in 1963 by Sandy Weinreb. And this is the 2 pi j equal to 3 by 2 ground state, which breaks up because of lambda doubling into 2 states, and which further breaks up because of hyperfine splitting into 2 more states. Each lambda doubled line breaks up into 2 states. And so you wind up with 4 different spectral lines within the ground state, which are at frequencies of 1667 megahertz with a lot of decimal places, 1665 megahertz, 1720 megahertz, and 1612 megahertz. These are called the main lines, and these connect lines with equal values with total angular momentum quantum number. And these are called the satellite lines, and they connect levels with plus minus 1 change in the total angular momentum quantum number. That turns out to be foundational for this work. In equilibrium, the 1667 megahertz line is a factor of 9 larger, stronger than both of these. And so the nice thing about 15 years ago, we realized that these lines arise from a combination of these two mechanisms, lambda doubling and hyperfine splitting, and that you can show fairly easily gives them different dependencies in alpha and mu. And that was nice, and so we wrote a paper on this. The catch was that, the depressing part was that, we know that OH in galaxies are never in thermal equilibrium. OH is a mess. It's excited all over the place, and so therefore, that assumption that I mentioned earlier, that if they are in thermal equilibrium, they will come to the same gas, just breaks down. So therefore, this seems like a cute idea, but which is useless. But it turns out there's this beautiful mazing and anti-mazing mechanism, which gives rise to population inversion in the f equal to 2 or f equal to 1 levels. And this results in what I call conjugate, or what are called conjugate satellite lines, which have exactly the same shape, but opposite sign. And I'll show you what I mean. This is an example of a conjugate satellite OH line in the local universe, at redshift 0.002. It was found about 20 years ago by Haupt van Langevelde. And what I'm plotting here is optical depth versus velocity. And so things which are positive in optical depth are absorption, things which are negative are emission, and this is plotted as a function of velocity over here. So you can see the 1720 megahertz line at a velocity of about 540 kilometers per second is an absorption, it is a narrow component. At exactly that velocity, 1612 is an emission. This continues to have a second component in absorption. At exactly that velocity, 1612 is again in emission. Suddenly, 7020 flips into emission, 1612 flips into absorption. No absorption emission over here, and boom, the opposite, 1720 in absorption, 1612 in emission, and a little bit of weak stuff. This, it turns out, is not a real emission. This is the GLONASS satellite, which is one of our nasty things that hurts us in astronomy. But what is really cute is that if I simply add each point up, I just take every point at corresponding velocities, add them, I get noise. These lines exactly cancel out. And now this is remarkable because the Maser mechanism is in situ at redshift of point of wherever the galaxy is. Which means now I have a mechanism by which I'm guaranteed the lines come to the same gas locally at that redshift. So now the issue is, can I find these lines at high redshift? So that's the game. These are quantum mechanical selection rules. I can tell you what these rules are later if you like, which give you 1720 emission and 1612 absorption, or vice versa, with exactly the same shape. So what happens, suppose alpha changes? If alpha changes, remember the line mazing mechanism is the local mechanism. The shapes will remain the same. The velocity axis will change because the redshift is wrong. All that will happen is that these lines will translate relative to each other. But I can always find a velocity offset such that if I slide the lines back by the right amount, they will exactly add up, they will exactly match. And if I don't slide them, I will find residuals over here. So if there are changes in alpha and mu, same shape, a linear translation. So about 13 years or so ago, we found two of these redshifted conjugate systems at a redshift of 0.25 and 0.77. And these are the first two known at cosmological distances. And we've been chasing after this system, actually, and this one also, but this one especially is kind of my pet for the last 15 years, ever since. So we used the Arecibo telescope, which is this gigantic object in Puerto Rico. If you saw GoldenEye, you'd have seen it there. It's 300 meters in diameter. It's the biggest telescope in the world, and size matters in astronomy. And so we used this telescope, and we observed this system for 125 hours, which is probably the deepest integration ever done with the Arecibo telescope. We took a crazy high velocity resolution, about 100 meters per second, and we did exactly simultaneous observations of the OH lines using a special backend. We applied the same data editing to both spectra. Spectra were exactly simultaneous, so no line variability. And these are probably the most sensitive radio spectra ever obtained. And that's what we got. The 1720 line is seen in emission. The negative things are now, this is now negative going up, if you like. 1612 is an absorption, and you see this weak feature over here, and actually even a weak feature over here. When you add these up, each point over here is at a resolution of 100 meters per second. When you add these up, you get perfectly conjugate behavior. There's no evidence of velocity offset, which is kind of depressing for us because we had a 2.5 sigma result which suggested changes in the constants before we got these deep data. So we used a cross-correlation approach because that allows us to go down to sub-channel resolution. And we applied the same approach to the Centaurus A data, the local galaxy, and we got the expected null result. And the final Arecibo result on this system gives you a velocity offset of about 70 meters per second, plus minus 50, which gives you delta alpha by alpha of minus 9.9 plus minus 6.6 times 10 to the minus 7, or a 2 sigma significance delta alpha by alpha less than 1.3 times 10 to the minus 6 over about 3 billion years. And this is the strongest ever constraint on cosmological evolution. This is where we are today. And so these are two other results and changes in mu, which are down by a factor of 10. We are about 10 to the minus 7 in both of these. That's the OH result that I just showed you, and those two are the mu results. So in summary then, I hope I've convinced you the studies of fundamental constant evolution allow you to test the standard model and also provide a window of on unification theories. We can probe changes in gigayear timescales with astronomy. And these are the two results. I didn't really talk about this one, but this is the result that I've talked to you a fair bit about. We have today no evidence, no statistically significant evidence for changes in the constants. We're going to improve by a factor of 10 on this result within a year, by about a factor of 100 over the next decade. Thank you.